Okay, here's a little update on our setup. Our power supply is now feeding the system. As you can see, I have no milliamps to read, and this is because we are running on microamps. Okay, the meter on the left I have set on milliamps. I'm simply using the meter's clip leads because the clip leads are still down in the workshop. Got the one set on milliamps, and it's on the negative side of the power supply to the negative side of the rail. This one here is set on microamps, which is on the positive side of our power supply to the positive side of the rail on the circuit. So as you can see, they're reading the same to the first two digits. The voltage on the power rail is at 10.46, 10.47. Our power supply says 10.5. We'll be losing some through the two current sensing resistors within the meters. One being of course set on microamps would be a fairly small resistor. Okay, that meter there is hooked across the negative and positive input on our power rail. So we have our 10.46 volts at our 412, 413 microamps. Now I've managed to stabilise the system. I was having a lot of trouble with what we would call our trigger coil that was sitting here before. Having to have it within half a mil from the two drive coils. If I bump the table even slightly, the system would stop or go out of tune. So we've solved this problem with the function generator. What I've got here is a one-to-one isolation transformer. Basically, I'm using one coil driver to drive right alongside the resonant frequency of the circuit. So it will be driving L2, which of course is our trigger coil, or the coil across the base emitter. Excuse me. So it took a bit of doing, but I got the frequency eventually. 5.81 kilohertz is the resonant frequency of this circuit. That is where we get our lowest power, power consumption for maximum power output, much like a tank circuit, only with current and not voltage. I'm using the square wave, but the forward side is set on 30%, and that has to be exactly 30%. I'll show you why very shortly, but that's pretty much well it. That's how I've managed to stabilise it. I'm just triggering that with our function generator at the frequency the circuit is happy at and the percentage that it is happy at. So this 30% on the forward side is critical, and so is the coil alignment on the two one-to-ones. So a bit hard to tune this circuit properly, but perseverance, and we get to where we want to go. Okay, so at the moment we're doing 410, 411 microamps at 10.4647 volts. Now on our output cap, which is of course feeding the circuit, we have 9.85, 9.86 volts This is due to our diode and resistor drop across the power rail. Okay, so 410, 411 microamps and our 10.46 volts. Now I'm just going to drop this duty cycle down 1% to 29. Now, although we use less current, our output also goes down along with our voltage across R2 here. So I'll click it back up to 30% on the forward side. Now you can see our current climbs, but the ratio on the output side that we get is a whole lot better. So now I'll go up by 1%. And once again you can see it drop back down. And of course here, across R2, we are losing once again far greater than what we are reducing the current input by. So there's 30% duty cycle on the forward side, and I've just hit 32 and the system stopped altogether. So that's how critical it is. So she's a very touchy circuit, but once I've set it at 30%, I can pretty much well chuck the probes anywhere around the place, bump the table, and we still keep on thumping along. I have it set on 2 volt peak to peak, 30% duty cycle on the forward side, at our 5.81 kilohertz. If I go 0.01 either way of that frequency, our old LED starts to splutter, our current draw on the input side goes up and our output goes down. So it's very critical, the tuning of this circuit. Our LED is extremely bright now. It's getting a bit over half brightness. So we're not going to take that into account. I don't like measuring light as some form of power measurement. So we're purely going to be relying on our scope across our 22 ohm resistor on the output side to tell us what's going on there, and of course our input readings. Okay, so the scope itself, we'll try and keep the camera still. I'll just freeze it so we can get an accurate look at it. So our peak to peak voltage is 6 millivolts. Our voltage max is 24.8 millivolts. Our minimum is 18.8 millivolts, which of course is this difference here. Now the reason we have a peak to peak voltage across R2 is because, as you can see down here, we have some serious RF across it. Now I've got the scope to average the readings out for us. Even though we're at 1.87 megahertz, we're well within the scope's range. It's a 100 megahertz scope, as you can see, so it will be quite happy making accurate measurements. So what I'm going to do is turn the average off and go peak to peak, and you can see the mess that this scope is sorting out for us. So that's the RF across our 22 ohm resistor. I'll freeze that for you. So you can see our peak to peak now is 26 millivolts. Our 36 millivolt max, 10 millivolt minimum, and our frequency 1.886 megahertz, and that does fluctuate. So wrong button. I'll just have the scope do all the work for us, so as we're not messing around trying to average out readings and that for us. And our circuit is of course running on our 9.86 volts. So there's our current input set on our microamps, and that is our voltage across the power rail. So we're about 0.04 of a volt out from our power supply, which we could of course be losing across our two shunt resistors in there, as I said, were our current sensing resistors. So that's it for the update. Fantastic results being able to fine tune this system with our function generator, and like I said, it took me a while to get our percentage sorted out. 1% either way makes a hell of a difference, as does 0.01 kilohertz either side of our frequency. I did try the pulse. It won't work on pulse. It needs the square wave to pull the coil in both directions as the system wants to do. So of course at 2 volts peak to peak, 1 volt on the forward side, we won't be putting anything back into the system. It's purely acting as a signal to drive the base of the transistor. So far so good. In fact, so far a little too good maybe. I don't really know how we're getting that kind of current across that resistor, so definitely a lot of research to do on this yet, and it'd be great if a couple of you guys could build the circuit yourself and see what is going on here. Cheers guys.